So Assalamualaikum. Today I will explain about the sampling and discrete signal. So as you can see here, before we going through it, we need to sample out our audio first. So on this slide, as you can see here, I will explain the process of sampling and converting the audio signal into the discrete signal. So as you can see here, the main objective of this is we want to convert the continuous time audio signal into the discrete time signal so that it can be processed digitally. So the input used in the project is an audio DSP dot wave. And then the output we analyze is the frequency spectrum and the time domain signal. So by using the MATLAB, the audio file is first we read it with the audio read function. And then the signal then is converted into the single channel by selecting only left channel, which is we want to simplify the processing by making the signal mono. So the sampling frequency that we choose is 8000 Hz, which is sufficient for speech and basic audio analysis. And then after the sampling, the process signal is saved as a noise audio.wave for the future reference. So the figure as you can show here is after sampling signal frequency domain and then in the time domain. So as you can we can observe the signal behave in both time and the frequency domain. So the step is important. This step is important because we want to prepare the audio data for the further digital signal processing and analyze in the later stage of the project. So that's all for me. Thank you very much.
Hi, I'm Lo Bao Liang. In step 2, I was responsible for the FIR bandpass filter design. Our main objective was to solve the noise issue we identified in step 1. The audio contained both low frequency rumbles and high frequency hiss. So a simple low pass filter was not enough. To fix this, I designed a bandpass filter using the windowing method. I selected the Hamming window because it offered a good balance by minimizing spectral leakage. I set the filter orders N to 50, which gives us a sharp transitions without introducing excessive processing delay. The most critical part was tuning the frequency. Through trial and errors, we found that the code switch intelligibility lay between 1000 Hz and 2000 Hz. I set the normalized cutoff to 0.25 and 0.5 relative to the Nyquist limit. This effectively isolates the voice while rejecting the Maudie noise below 1000 Hz and the static above 2000 Hz. In MATLAB, I implemented this using the FIRL command with the bandpass argument. As you can see in figure 2, the impulse response is symmetry. This symmetry confirms that our filter has linear phase, ensuring the voice signal is not distorted during processing. This design provided the stable filter coefficient needed for the next stage, the stability analysis. So I think that's all from me. Thank you.
This part shows the pole zero port, which is used to analyze whether the design filter is suitable or not. First is the objective. The objective of this part is to analyze the stable of filter using the Z transform and the pole zero port. Instead of only looking at the time domain or frequency domain, we analyze the system from the Z panel point of view to make sure it can work properly. Next is the input. The input is the filter coefficient obtained from the window method. This coefficient was calculated during the filter designing process and are used for Z transform and pole zero analysis. Then is the output. The output is pole zero port in the plan. From this plot, we can observe the location of the zeros and the poles, and together with the region converge or RZ, we can determine whether the system is stable or not. The figure on the right shows the result. From the plot, we can see that all poles are located as the origin, which is a typical characteristic of an FIR filters. These zeros are distributed over the unit circle and are used to control the frequency response. Finally, the conclusion. Based on the Z transform and how they analyze, the design filters is stable and suitable for audio signal processing applications.
Now we're going to step 4, DTFT, discrete time fourier transform, and the spectrum analysis. The step 4 is to view and analyze the frequency spectrum response for the bandpass filter. And the input and output of the discrete time fourier transform is in frequency spectrum. Now we're going to see what is the mechanism that we're using. The mechanism that we're using the frequency Z, BA 1024 and FS. For B is the numerical coefficient on the step 2, and the BA is the denominator coefficient, and the value is always 1 because we design for the FIR filter. The 1024 is the frequency resolution, and the FS is the sampling frequency. The feature is our result of frequency design is the bandpass filter from the 1000 to the 2000 Hz. And the upper one is the region for our bandpass region, and otherwise is the bandstop region. So now we already verified what's the FIR filter, so we're going to the step 5 convolution.
Okay, so step 5 is convolution. So the objective is to remove noise from our audio by applying a bandpass filter between 1000 to 2000 Hz. and to keep the speech frequencies and also remove the noise. So we have three inputs here, which is X, which is our noisy audio, B, which is the filter coefficients, A equals to 1, which is the filter denominator, and our output is the Y clean, which is the filter audio. So the convolution formula is actually equals to yn equals to xn convolution hash n. So this means our xn is our original audio, and the hash n is actually the filter impulse response. So the operation actually slides the filter across every sample of the input. So our input xn is actually has 17,509 samples, and the filter impulse response that we use is actually has 51 coefficient, and after slide it will multiply and sum to produce each output sample. So at the right you can see that the 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 graph which is the unfiltered signal versus the filter signal. So on the top, this is the unfiltered signal. You can see that the audio signal is very noisy, has many fluctuations, and after we apply the filter, you can see that the noise has decreased significantly and the fluctuations has decreased significantly. So that's all for my part. Thanks.